Thanks a lot for Xiaoming for the nice introduction and inviting me to give this talk. So my talk will be about about quantum network. So it's mainly about quantum key distribution network, and in the end, I will further extend it to general quantum network. So this talk will be quite introductory. I won't go into too much details. Instead, I would like to call your attention that I know that many of the audience are from the classical information side. So this kind of work could be interesting to you guys. Okay, hang on. Okay, so first I will give a brief introduction about the QKD and the network. Then I will talk about some of the exciting current implementations, mainly on the QKD area. Then I will talk about when we go from the point-to-point QKD to quantum network, QKD network, what kind of problems, what kind of practical tasks we need to solve in those kind of practical scenarios. Then I will give a brief conclusion and then outlook. Background. So cryptology, okay, I assume that many of you are more experts in this kind of area. So it's very old science science in a long time. So cryptography basically just the science of encoding and decoding. So the key point that we need to have a key to do the encoding and decoding. And then we know that a cryptography, in the cryptography, key is pretty much everything. So basically the security mostly lies on the key. So a key basically is just random bit string. So we need a good random number generator to generate this key. Okay, so we do have a quantum random number generator to do that. And also, if we really need a key for communication, so for those symmetric key crypto system, private key crypto system, we need the key to be identical between Alice and Bob. Okay, so that they can do the faithful encryption and decryption, and also the key must be private, so that no hacker can know the key ahead. So there's a big problem in the field is the key distribution problem. So for example, if we talk about the one-time pad encryption, then we need the key to be as long as the message. So we do need a very efficient way to distribute the key. All right, so I will very quickly go through this quantum key distribution, BB84. So it's published in 1984. Even today, we are still mostly, we still, our current implementation of QPD mostly still depends on this protocol. So the idea is quite simple. I just prepare a bunch of states. Okay. Okay. So bunch of states. So so let's say let's talk about polarization. So if we talk about the states, then for example, we have 4 polarization: horizontal and the vertical, and the 45 degrees and minus 45 degrees. Okay, so then we call there are 2 bases. One is the rectangular basis, horizontal and vertical, and then also diagonal basis. We call it X basis, X and the Z basis. And it's basically randomly pick up this 4 states and then correspond to the random key. So in this example will be 0, 0, 1, 0, 1, 1, 0, 0, and then send to Bob. Just through a quantum channel. So this channel is insecure. So in principle, we can even assume that in the worst case scenario, we can even assume that this channel is fully controlled by an eavesdropper. So after Bob received these signals, this quantum state, Bob performed the measurement. So we know that in quantum mechanics, when we perform the measurement, we need to specify the measurement basis. So in this case, he randomly chooses X or Z basis. When we say X basis, it means looks like X, right? So it's diagonal basis. Z basis, we call it the vertical and the rectangular basis. And then perform the measurement. So there's some property of the quantum mechanics I can quickly say. For example, if Alice send the state in the right basis, in the same basis as Bob, then the measurement results will be the same between Alice and Bob. So for example, the first state, Alice sent out horizontal. If Bob try to distinguish whether it's horizontal or vertical, Bob must get the horizontal. Okay. But if we look at the third state, the third case, so Alice sent out the horizontal again, but Bob measured the wrong basis in the x basis, then his results will be random. Okay. So basically, so in this case, some of the Bob's results is random. Some of the results will be same as Alice. Then next step will be Alice and Bob, they use some public channel to discuss that whether they choose the same basis or not. They threw away those detection results, like those data, when they choose different bases, and then only leave the cases, the raw key as when they choose the same basis. So in this case, it will be so this red ones will be the wrong basis ones they just threw away. The rest ones, they will share the same state, the same key, 0, 1, 1, 1, 0. Okay, so it will be the same. Okay, let's take a quick look at it's also shown in the original paper. So if Eve performed some attack, okay, let's talk about a very simple attack. So Eve performs measurement. So she tries to get the information from the Alice state. Again, same as Bob, Eve does not know ahead what's Alice's basis. So what she can do is that, one naive attack will be Eve perform the measurements, randomly choose the basis and get the state. And then after performing the measurements, and then Eve can resend the state to Bob. So in this case, let's talk about let's look at the first state. So in this case, Eve is not lucky. Eve chooses the wrong basis, X basis, but Alice Bob chooses the right basis, Z basis. Then in this case, Eve will jeopardize the state. So basically, originally, Alice sent out the horizontal, but after Eve's measurement, she projects the state to the diagonal basis. Let's say for this case, 45 degrees. And then when Bob gets this state, perform the measurement, his results will be random. So for this case, condition on Alice Bob choose the right basis. If Eve perform this attack, then Eve has a 50% chance she will mess up the state, get some random state. So in the end, Alice Bob will figure out that, okay, there's a bunch of the errors come up in the channel. So Alice Bob will know, okay, someone attacks. They throw away the data and then do the scheme again. So basically, this is the basic idea of QPD. Condition on the case that the Alice Bob, they figure that the error, so the error rate is lower than some threshold, some bar, the error bar, then they can be sure that the final key will be secure. Okay, so that's the basic idea of QPD. Okay, so I won't go into details. There were lots of developments in the past few decades since 84. So we make this QPD protocol very practical, and also we have a very fast encryption and encoding and decoding system. Okay, so later on I will show you some of the results. So let me before I go on, then let me just quickly give you some idea about this QPD. So I don't want to so this is because I don't want to oversell this idea of the QPD. So first of all, in the QPD, random keys are distributed. So only random keys are distributed. So QPD is not really used for information transmission. Okay. So Alice does not send the message directly. Since it's random key, so users, they can just throw away the key if they figure that the key is not secure. Okay, and also those keys need to be used for later crypto system like one-time paired or authentication. So this requires this we call the composable security definition. And then also I want to figure that what's a successful attack by Eve. So Eve can obtain non-trivial amounts of information. So non-trivial is basically just epsilon language. Okay, so this is related to this composable security definition. Okay, about the final key without Alice Bob's notice. So if Alice Bob in the end they don't get any secure key, so this attack is not successful attack. Okay, and also we assume the channel is totally secure. So basically that means that the quantum channel basically Eve controls the quantum channel. You can even think of you send a state directly to Eve and then you put somehow make some operation and then send the state to Bob. And also we in the later data post-processing, we need some discussion between Alice and Bob. So in that case, we assume authentication. It's the channel is authenticated. Okay. Okay, so the security of QKD or quantum cryptography is based on quantum mechanics. It's quite solid. Okay. So basically, the security level is really we call it information theoretical security. Okay, we can reach that. And also, it's of course it's secure against quantum computing and so basically any computational power. But I need to emphasize that QKD cannot replace current crypto system. Okay, that means that many other tasks like authentication, signature, they already done very well with classical means. Okay, it's really just so today when we talk about cryptography, it's basically mainly just we produce two things. One is key distribution, one is a random number. Okay, and also sometimes we also call QKD as a quantum communication. But we really cannot replace classical communication at this moment. Okay, actually, in the foreseeable future, we are still doing this classical communication. So in the end, what I'm trying to say here is I don't want to overclaim the quantum cryptography at the moment. So this is if you think about that, quantum cryptography is just a nice extension of current classical cryptography. It could be very useful to be patched to the current crypto system. All right, so let's take a look at the what kind of system we are talking about. So this is a picture I took a long time ago, almost more than 15 years ago, when I was a PhD student in Toronto. So this is the box we're talking about, Alice and Bob's box. So this one box will generate those quantum states like a 0, 1, plus, minus. Okay, or in the polarization, it's a different kind of polarization. Bob can perform the measurement on X and Z basis. Okay, so that's the picture we are talking about. So those two boxes, actually, even 15 years ago, we bought those boxes, okay, directly. So it's a very practical field. So there were quite a few commercial QKD companies. Okay, so they are selling these QKD devices like a month ago, maybe, Quantum C-Tech, it's become public, right? It's a public company right now, okay? So it's a very practical field. So we already have the products, we already have the device, okay? And also, so again, so what do we just discuss? It's like, it's point to point, always adding Bob to the key distribution. Of course, in the real implementation, we need to make it compatible with the network, QKD network. So there are lots of implementations, even long time ago, like this implementation is 2004. Lately, US they put lots of much more money on this field. They try to establish this. Later, I will come back to this point. They call it the quantum internet. Okay, so make it sure it is secure. Okay. The underlying the security guarantee is the QKD. And also we have a Tokyo network. It's already quite a few years ago, 5 years ago. So for this Tokyo network, they invite a lot of companies to come over and then just plug in their device, different kind of QKD devices, and then make the network works. And also there's some company, Mitsubishi, they try to connect the cell phone with the QKD. So basically, you have because the QKD device is huge, so there's no way you can carry it. It's not portable. So what you can do is that you put that device in your office or at home, and then there's a link. You can put your cell phone to this device and then download the key. So the key is classical. So then you can use the key later on. Okay. So here, so with this picture, so the classical communication is not limited by the quantum QKD speed. Okay. And then there's a huge European network, and then they are also expanding this network. Switzerland, more than 10 years ago, they already use it for the Swiss election. So there's there's a very big group in Geneva, Nicholas Gisen's group. They built up a very nice network around the area. And also I heard that it's a confidential information. So there were some talks that they mentioned that some of the banks, they use this QPT network. It's very nice implementation. Also, South Africa, they also built up this field test for the QPT network. Melbourne, okay, so I won't go into details for all this network, but if you look at the time stamp, so it's already like 10 years ago. Okay, so in China, we also have quite a few implementation in this area. So one of the big ones is the backbone construction between Beijing and Shanghai. So in this backbone between Beijing and Shanghai, there are 4 urban network. One is in Beijing, Jinan, Hefei, and Shanghai. Okay, so with this backbone, it connects this whole link. Okay, it covers a very big amount of the economics of China. The construct is already done in the end of 2016, and so it's continuously running. Even today, it's still running. Actually, if you go to Shanghai, USTC Shanghai branch, there's one big exhibition area. You can see those screens with this check down all the keys distributed between these nodes. It's a very nice demonstration. It's very nice implementation. And also there are some companies that they already use these keys. Okay, so that's a picture. And of course, even if you go further away, if you want to do the communication between, let's say, between Shanghai and let's say Vienna or Geneva, then it's still too far away, because if you want to do this transit node, go to Europe, that's really far away. Okay, what do? We use a satellite. Okay, use a satellite. Okay, so I will talk about satellite later. So actually, there's after this backbone construction, there were also plans to do much more. So basically, this picture shows some of the data centers in China. So the idea is to try to in the future, that one big future plan is to try to connect all these data centers with the backbone construction. Then it's really highly secure network. Okay, but still there's some points it's really far away. Okay, so far away. And also if you think about it, if you go to Europe, and then it's even further away. So this kind of backbone construction idea won't work too much. So that's why we talk about the quantum satellite. Okay, so the first quantum satellite is launched 4 years ago, exactly 4 years ago, like it's August, right? And then they use satellites to connect this kind of do this intercontinental key distribution. Okay, so there were 3 missions for this quantum satellites. One is to do the QPT in the 1,000 kilometer this 1,000 kilometer region. The other one is to do the intimate distribution. Intimate distribution is very important. It can be a very big part of the quantum network. Later on, I will briefly mention that in the outlook. Also, quantum teleportation. Quantum teleportation is a kind of quantum communication. It's a really fancy idea, but of course, if we and also it is secure. It is secure to do the communication. Okay, in the future projects, it will be like we use quite a few satellites to connect these big networks, and then within the country, we use big backbones to connect these cities. Within the city, we have a urban network. Okay, so that's the idea. So pretty much the same, similar to the current internet. So this those few slides and the pictures come from the USTC. All right, so what's the example? I'm a theorist. So what's my job? What's my job? What kind of practical task in the QPT network? So when we go to the quantum network, so if it's ANSYS-BOB, it's very easy. It's quite easy. But if you go to if you look at the urban network, like 50 dozens of nodes, then the network is already quite complicated. It's more complicated than what do we expect? When we say we, I mean the physicists. Okay, so a lot of problems pop up. Okay, so we need to really separate to do this those practical infrastructure. Then we really need to separate this network structure. So this network structure is very similar to the current internet. Okay, on the first level it will be host level, host layer. So basically the users will do the interface. Okay, you really get the key to yourself and do the encryption. Below that, it's the key management layer. Okay, so we need to do the key management. Then we talk about the quantum network layer. So whether you do because in the quantum network, so you need to figure out that whether these two, whether this link need to work or need to sleep. Okay. Finally, on the bottom one is the QKD link. So basically, that's the one we talk about in the previous slides, like a point-to-point link. Okay, what's the practical task? So there are lots of network issues here: latency, reliability, scalability, cost, and also security, key consumption. Okay, so there are lots of these kind of very similar issues in the current network. Okay, let me here in this talk I will focus on two very simple examples. One is talk about the security. So in the network, let's assume that for the moment, let's assume it's a trusted node network. So basically, in the network, in the node, so basically it's the from the urban network. Okay, there are lots of nodes in the city. We trust the node, but some of the nodes may be compromised. Okay, where the keys are insecure. Okay, so basically we in general, so in theory, we assume we trust all the network nodes. But in practice, it's important to figure out how much we really need to quantify this trust. So for example, people can ask a question: if one of the nodes is insecure, okay, let's say it's compromised, does that mean that the whole network is insecure? Okay, so we need to talk about that. Kind of issue in the practical case. Second one is the key balance between the key distribution and the consumption. We know that QKD, the speed of QKD normally is slower than the classical computation. Okay, so then how can we balance that? Okay, I will talk about these two issues. Okay, so there are different kind of network topology. Okay, so there's like a backbone network. So basically, backbones will construct these big networks, and then there's a backbone links. There are also star type network. Everyone will connect to a trusted node. Okay. And then, okay, in general, the topology could be quite complicated. Okay, let me talk about the first case. Okay, compromised node. Okay. So let's say we have a very generic quantum network. Okay, so the connection is quite complicated. Okay, so we want to say that there's some, let's say, between Alice and Bob. So there's one message I want to send from Alice to Bob. I want to make sure that this message is really, really secure. Okay, so now the question is so suppose if some of the nodes are compromised, can we still make it secure? Okay, now let's talk about so that's from the user point of view. Let's talk about the attacker point of view. So from the hacker point of view, okay, so what's the strongest attack in this case? Okay, so let's assume in this case, that if job arbitrary nodes, okay, and obtain their key. Okay, the strongest attack let's assume if tries to attack Alice and Bob. So this is Alice, this is Bob, and then try to attack this Alice Bob's communication. Then the strongest attack forms a cut in the graph. Okay, forms a cut. So when there's a cut in the graph, then there's no way for Alice and Bob to do secure communication. Okay. Of course, for each strategy becomes a minimum cut problem. Okay, in the graph state. Okay. So from Eve's point of view, she needs to attack the minimum amount of the nodes so that she can form a cut, such that Alice Bob cannot do such that Alice Bob's key distribution is insecure. Okay, then we talk about the high security one. Suppose we know that if the attack, so if the compromised node forms a cut between Alice and Bob, then there's no way you can get the security. Now the question is, what if it does not form a cut? Okay, then can we do the secure communication? The answer is yes. So this is we call it the communication with the highest security. Okay. So in this case, how can we do that? So let me just take an example here. So the idea is quite simple. So Alice will broadcast the exclusive or the results of all the keys of the links. So each link represents the each edge represents the QKD link. Okay. So this is the QKD link. So basically, one link means that these two nodes they share one secure key. Okay, it might not be secure due to compromised nodes. Okay, if it's not compromised, it means secure key. Okay, same here. So Alice will broadcast all the key information. So XOR results of all the keys, and then broadcast to everyone. And then actually everyone else will just broadcast all the keys. Again, it's the same. Bob will do the same. Then Bob connected to all the keys, Bob can recover this message. Or you can think of this message as another random key. Then as Bob can establish this nice key. Okay. So this is why we can prove that as long as if compromised node does not form a cut between Alice and Bob, they can do the secure key distribution. Okay. So this is the highest security because as we know here, if it forms a cut, there's no way you can get the security. Okay, so it's kind of a high security. Okay, so this is a quite simple example. Okay, so simple example, and also it's useful in reality. Another one is the balance. We try to balance the key distribution and the consumption. Okay, so we know that the secure key is a limited resource in the quantum network. We know that the QKD. Typical QKD's key distribution speed is the 1 Mbps. B is the bit per second. Okay, but we know that's our cell phone or the 5G. Okay, so my cell phone is the 4G, but if we talk about the 5G, we are talking about the hundreds of 500 megabytes per second, right? So it's the 3 orders higher than the QKD. So in this case, QKD definitely is a limited resource. Okay, so we need to balance the key assumption between all nodes because if you form a big network, go from the for example, if you do this what we just talked about with high security, then the key cost is huge, right? So all the nodes will cost a lot of key, right? So between Alice and Bob, we need to really so that's 2 users because there are a bunch of other users want to do the communication, right? So how can we do the balance? Okay. First of all, we need to model this picture. So here, for the moment, let's assume that the shared key basically is the same as the transfer message. We will talk about in this talk we'll talk about the transfer message, but it's really you can think of it's just key distribution between Alice and Bob. Okay, so how much data you want to transfer, and for the channel, how much key can be stored or how much key can be generated. Okay, for the key distribution. Okay, so we apply some very typical classical network result. Okay, so what's the constraints here? So for each node, it's like you have new data coming in. You have new data coming in. So new data request. Okay, so for this node, I want to send out something, and also I have some key generated. So use the key. So then I can use those key to send out the data. Okay. So it's it's very similar to this network problem. We call it the dynamic queue problem. Okay, so we want to make sure that the data requests won't pile up infinitely. Okay, so that's the stable case. Okay, from the key side, it's relatively easy. So basically, it's just key generation and the key consumption. Okay. So you don't want to so this key storage cannot be negative. Okay, as long as it's positive, it's fine. Okay. Okay, so in this case, so the number of channels, so because a bunch of the channels will, in the complicated network, they will work simultaneously. Okay, so there's a big constraint on the threshold. Okay, so in this case, it's okay. Let's see. Okay, okay, I think I can explain a little bit. Okay, so for this one, so basically it's like for this network, so because we can basically, it's like because from when we do the communication, actually it could be like from the too far end, right? And it's send some states too far, but it will go through one by one, right? Depends on your scheme. Depends on scheme. For the most secure one, then you need to really go through all the nodes in the network. So your request will be very, very high. Okay. Oh, so here's my colleague, Long Bohuan. So he's from the classical network side. Okay, so it's and also we need to talk about the network stability. Okay, so we don't want the residue data go to infinity. Okay, so it must be bounded. Okay, must be bounded. Okay, it's well defined. So basically, we convert this key management problem in the QKD to a very well defined problem in the network. Okay, then also we use exactly the problem, exactly the solution from the network to solve this problem. Okay, I will skip the details. Okay, so this is a very typical network problem. Okay, the result will be okay. How much key you can consume, and then what kind of communication, what kind of key consumption communication you can support for this network. So this kind of question is very, very important in the QKD network construction. Think about that, for example, they have a big network. Everyone wants to use the key. Now the question is that, or maybe, for example, let's say you want to build up a network in a new city. Then one question the customer will ask is that what kind of communication this network can support. Okay, so that's the result we are talking about. Okay, this optimization result will give us these questions. Okay, what kind of support, and also what kind of key management scheme we should perform. Okay, of course, in reality, so this is a very idealized situation. In reality, we have many more problems. Okay, some of the nodes are more important than the other nodes. Some of the nodes are more secure, and also some of the links are much faster. Okay, so here I will give a quick conclusion. So today QKD becomes and also random number generation becomes very, very mature. Okay, so you can really purchase those devices from the companies, commercial companies. And so if you really want to use those devices to build up a network, then there are lots of network issues come up, mainly involving the key management problem. So we can apply this counter graph theory techniques to QKD, and also those network techniques to the QKD network. Of course, we can in the future we are dealing with more complicated network. So the previous one is pretty much like a very classical network, because we have the QKD link. Once the QKD link is done, then the key becomes classical. Everything becomes classical. But in the future, for example, later we already have a demonstration. So we can entangle two quantum memories between two nodes. So we know that's so basically in the future we really talk about those links. So those key might not be really classical key. After key distribution, after entanglement distribution, the two quantum memory is entangled. So you can think of those can be used for later communication, secure communication. So those key could be quantum. Okay. So this kind of issue becomes much more complicated. Okay. So when a quantum network with entanglement, so for example, for this network, so there are lots of repeaters over there. So you can do the repeaters. So repeater is the same as the classical network repeater. So with entanglement swapping, you can really swap the key without trusting this node, Okay. And for network, we can hybrid this untrusted node with the trusted node. Untrusted node means that so that node performs some operation. You don't need to trust the node. Okay, so it can be performed by the if job. Trust node, you really need to trust it. Okay, so then the network becomes a big, massive issue. So because the quantum network, this kind of swapping, like the XOR in the what we discussed in the first example, that kind of swap becomes that kind of XOR becomes swap in terms of swapping in the quantum network. Things becomes quite complicated, and also routing is not trivial. For example, previously in the first one, for example, in the first for this picture, the high security, we can simply say we just can publicly announce all the results. But in the quantum case, we don't have this kind of public announcements, this kind of thing. So when you do the swapping, you can only entangle these two nodes together. Okay, so it becomes evolve this. How can you have to really talk about the routing of this entanglement swapping idea. Okay, so again, so this is a quite open area. So you can see that the paper is published last year. So it's quite open. So we need and also for example as a physics, I'm from the physics background. So we do need a lot of people from the other background to solve these problems. Okay. All right, so that's pretty much all for my talk. So I hope that's this is more like an introductory talk. So I hope that it can inspire some of you can join the field and to do the solve the network issue. And here's my group, and some of the slides are presented by my group members. Thank you.
Thank you, Xiongfeng, for the excellent talk. Large group. Okay, so are there any questions from the room? Anyone who want to ask question can unmute yourself. Okay, maybe first I will ask a few technical questions. I'm really like the idea you mentioned last. I mean, the entangled network, not compared to the classical network. So does that mean in some sense we can entangle the two paths? Because you mentioned that if there's a max cut, big cut, then definitely it's not secure. But if we are able to, in some sense, entangle the two paths, can we against the mean cut attack?
Sure. So the idea is for this one. So when here they put two kind of nodes. One is they call trust node. The other one is a repeater. So trust node is really something what we just discussed. So we really do trust it. If it's not there, if it forms a cut, there's no way you can get security. But there's in between. There's also a bunch of the repeater. So this is you can think of untrusted nodes. Untrusted node is like so those nodes we don't really need to trust those nodes. So basically, if can get all the information from the node, but still we can guarantee the security. So combination of these two kind of network will make the network more robust against the if attack, because there's no way we can guarantee that one node is secure in reality.
Okay. So
yeah, definitely. So basically, this kind of hybrid system will be very interesting.
Another question is also related to the entanglement. So about the K, I mean the other topics in your talk. So is it possible to do some entangled private key? I mean,
yes. So basically, it's like so if we think about that, there's a secure key in the quantum scenario. What does it mean by secure key?
Yeah.
In the quantum scenario, you can think of it as an EPR pair.
Okay.
Okay. Actually, one EPR pair is definitely. So normally we just say from the resource point of view, it's larger equal than one secret key, because if Alice Bob gets one EPR pair, perform sigma z measurement, they will get this it as one pair of a secure key bits.
Yes.
Okay. But of course, quantum EPR pair can do more, right? For example, let's say teleportation. Okay, teleportation. Yeah. Teleportation is also secure, so they can teleport a quantum state directly from Alice to Bob. They can do, let's say, in the future. Let's say, for example, I didn't show you in my slides. For example, in the far future, not too far future. Let's say in 10 years, we do have some company like Google. They do have this quantum computer. But not everyone has a quantum computer. So sometimes, for example, I want to do some calculation with a quantum computer. So I send some requests to Google. So I want to make this communication secure. So we are talking about the blind quantum computing. Okay. So and also there's some discussion about the homomorphism and quantum computing, something like that. So in that case, this kind of we call the EPR pair becomes very, very important. So basically, if we can do this teleportation, go back forth, and then we can do this. We call it, let's say, blind quantum computing. Okay. It will be very interesting. Again, it will be a part of this big quantum internet. Of course, we'll make this quantum network much more complicated.
Yeah. I'm thinking, the routing, how to route.
how to routing this entanglement. Yeah, that could be quite challenging.
Yeah, lots of great questions for students. Okay, are there any other questions from other audience? Okay, if no further question, I think, okay, let's stop here. Thanks, Xiongfeng, for the really nice talk. Thank you.
Thank you.
And also thanks for attend this quantum session. I think this is the end of this session. Thanks to all the speakers. Thank you.
Thank you.
Thanks
Bye-bye.
for all the audience.